Brian's logic discovers the globe horizon. Dip angle is double eye height. Recently, Brian's Logic released a video entitled Globe Non-Refraction Fraud, linked in the description. In it, he discovers that the dip angle to the horizon translates to twice the observer's height. Let's see if we can derive this from first principles using Euclidean geometry and a little bit of trigonometry. Let's start with three perpendicular lines. Two lines perpendicular to a third line are parallel. Let's add a transversal. Alternative interior angles, marked here with theta, between two parallel lines are congruent. Now let's zoom out and relate this to the globe. The observer is in the upper right vertex with an eye height of h. The pink line is now tangent to the globe, meaning that's the distance to the horizon. The observer must look down slightly to see the horizon, with a dip angle of theta, measured relative to the observer's horizontal. The orange line at the horizon leads back to a spot beneath the observer, forming the sagitta. This diagram is mathematically correct, but the angles and distances are greatly exaggerated. In reality, the dip angle theta is less than, often much less, than 5 degrees. Please notice that with very small angles of theta, the pink distance to the horizon will be essentially the same as the orange distance to the sagitta. Now, what did Brian discover about the globe? Before proceeding, I just want to emphasize that this diagram is just to make things easy to see. Look at the angle at the very top of the screen. This is actually a 1 degree angle, and this represents the dip angle for an observer with an eye height of 1,200 meters. The examples Brian gave in his video were far shorter than that. His primary example was for a viewer height of 35 feet, resulting in a dip angle of less than 1/10 of a degree. Another example had a viewer height of 500 feet, resulting in a dip angle of about 0.4 degrees. He then plugged this dip angle and the distance to the horizon into the classic angular size calculator. When dip angle and distance are matched, the projected size is about twice as big as the viewer height. This sounds like an awfully big coincidence. So what's really going on? Returning to our original diagram, what Brian has discovered is that the sagitta under the observer's position is equal to the observer's height. When you add them together, you end up with double the viewer's height. Again, this is for really small dip angles, less than 5 degrees. Before continuing, let's look at one interesting aspect of small angles. Let's take a right triangle with a 1 degree angle and a hypotenuse of 1 mile. What's the length of the short leg? We multiply the hypotenuse by the sine of 1 degree and get 92 feet 1.8 inches. Now let's repeat it with another triangle, this one having the long leg be 1 mile. This time we multiply by the tangent of 1 degree and get the short leg of 92 feet 2 inches, a difference of 2/10 of an inch for a triangle that is a mile long. So let's relate this to the Earth, again with very small angles. If we start on the right, touching the Earth, and project a horizontal to the left, we'll get a bit of curvature drop, shown in blue. This is equal to the sagitta height. Or we could start on the left, with an observer at some height. He can look to the horizon with his gaze tangent to the Earth's surface. So let's compare the globe Earth to the flat Earth. As we've shown, with the globe Earth, curvature drop is equal to the sagitta, which for small dip angles is equal to the observer height. Therefore, if we plug in 35 feet, observer height, we'll get a distance to the horizon of 41,000 feet and a dip angle of about 0.1 degrees, as we mentioned before. Now we can plug those outputs into an angular size calculator, and we find the size to be about 2 times 35 feet, or about double the viewer's height. This makes perfect sense on a globe. But what about the flat Earth geometry? Well, it's not really clear how it's supposed to work. The observer is looking down with a dip angle twice as large as needed to see a horizon 41,000 feet away. And why is there a perfect 2-to-1 ratio between observer height and the result from the angular size calculation? It made perfect sense on a globe, but it makes no sense on a flat Earth which has no sagitta. We can repeat the process with Brian's other example of a 500-foot observer height. This time, the resulting size is 1,000.3 feet, making perfect sense for a sagitta almost identical to the observer's height, just as the globe geometry predicts. And again, it makes no sense on the flat Earth that we would look down with an angle twice as steep as we would need to see a far horizon at 29.6 miles away. So, thanks, Brian. It looks like your logic has once again proven the globe. Thanks for watching, and as always, please be kind in the comments. Bye.